Boiling point and solubility of alkanes. Boiling point of alkanes, if you look at the boiling point of methane, it's negative 161 degrees Celsius. Methane contains 1 carbon. And the boiling point of butane, which contains of 4 carbons, is negative 1 degree Celsius. So the boiling point of alkanes increase as their molecular size increase, or you can say as the number of carbon atom increase, the boiling point of alkanes also increase. This is because the bigger the molecule, the larger the surface area that it has. When the surface area is larger, more van der Waals forces can be formed between molecules. Thus, van der Waals forces exist between molecules become stronger. So, if we look at the boiling point, we're looking at on the breaking of the van der Waals forces. Van der Waals forces is between one butane and another butane molecule. So, in 1 mole of butane, you have a lot of butane molecules in there. So, boiling point, we are looking at breaking the van der Waals forces between one butane and another butane molecule. So, when the surface area is large, more van der Waals forces can be formed between the molecules. Thus, van der Waals forces exist between molecules become stronger. More energy needed to overcome the strong van der Waals forces. Effect of branching and boiling point of alkanes. Pentane, 5 carbons in total, no branch. 2-methylbutane, also 5 carbon, it has 1 branch. 2,2-dimethylpropane, 5 carbons in total, but it has 2 branches. So, if you have to explain the effect of branching, make sure all the compounds or all the alkane have the same number of carbon. For isomeric alkanes, the presence of branching lowers the boiling point. If you look at pentane, 5 carbon in total, no branch, 36 degrees Celsius. 1 branch, the boiling point is lower. 2 branches, the boiling point is much lower. So the presence of branching lowers the boiling point only if the number of carbons are the same. This is because branching reduces the surface area and the molecule becomes more compact. So here, 2,2-dimethylpropane has smaller surface area than pentane. No branch has bigger surface area than branches. This is because all this side is exposed. But all this carbon is exposed. But for this one, this carbon is blocked by this 1 branch. This carbon in the middle blocked by 1, 2, 3, 4 branch, 4 carbon. So when the surface area is reduced, means the alkane that has more branch, less van der Waals forces can be formed between molecules. So the alkane that has more branch has smaller surface area. When the surface area is small, less van der Waals forces can be formed because this carbon in the middle is less exposed than all this carbon. This has more exposure to the outside. This one has less exposure, so surface area is smaller and more branch. Less van der Waals forces can be formed between molecules. Thus, weaker van der Waals forces exist between the molecules in this 2,2-dimethylpropane. Less energy needed to overcome the weaker van der Waals forces in 2,2 dimethylpropane. That's why it has lowest boiling point, because it has the most branch. Next, if we compare butane and 2,2-dimethylpropane, this butane has no branch. This 2,2-dimethylpropane has two branches. Previously, we know that more branch, less boiling point, lower boiling point, more branch, lower boiling point. But this one, more branch, two branch. This one has no branch at all. But this one, two branches. But the boiling point is higher. As I've mentioned previously, this effect of branching only for the same number of carbon. If you compare between these two alkane, 2,2-dimethylpropane has higher number of carbon. If the number of carbon is higher, it doesn't matter whether it has branch or not, it will have higher boiling point. More carbon, higher boiling point. Boiling point of branch alkane is higher than straight alkane if the number of carbon is greater. So it doesn't matter. First, the priority, look at the number of carbon first. If higher number of carbon, then higher boiling point. If you want to look at the branch, make sure the number of carbons are the same between the alkanes that we want to compare. Boiling point of straight versus cycloalkane. When comparing the same number of carbon, cycloalkane has slightly higher boiling point than alkane. This is because cycloalkanes in planar structure. So it's in planar structure, larger surface area and stronger van der Waals forces. So the structure of the cycloalkane makes it to have larger surface area and stronger van der Waals forces, therefore high boiling point compared to the straight chain alkane. Solubility of alkane. Alkanes are non-polar molecule, while water is a polar molecule. Non-polar molecules are soluble in non-polar solvent only. Meanwhile, polar molecules are soluble in polar solvent. So if you put alkane in water, if you put the non-polar alkane in polar molecule water, alkanes are insoluble in water because water is polar, alkane non-polar. Only non-polar can dissolve in non-polar, only polar molecule can dissolve in polar solvent. Alkanes have very low polarity in water because it unable to form hydrogen bonds with water. If you want to look at the solubility, make sure to explain about the hydrogen bond. If it is able to form the hydrogen bond, it is soluble in water. If it is not soluble in water because it is unable to form hydrogen bond with the water molecule. Alkanes are soluble in organic solvent of low polarity because the alkane can form van der Waals forces between alkane and organic solvent, means the non-polar solvent. Organic solvent is the non-polar solvent. The examples of organic solvent or non-polar solvents are benzene, chloroform, tetrachloromethane, and other hydrocarbons are organic solvent or non-polar solvent.